And hello once again, and thank you for joining our workshop on generative forecasting, the power of graph transformers in time series prediction. I'm Kitty Ivanovska and I will be your host today. In this online workshop, Jan-Erik Lenssen and Sally Liu from Kumo will explore how graph transformers powered by relational data are reshaping the way enterprises forecast. We'll walk through end-to-end forecasting pipeline built with graph transformers, showing how to generate more accurate prediction by combining temporal, relational, and contextual signals. You will also learn the difference between predictive and generative approaches, see real-world use cases, and understand how this method improves performance across forecasting tasks. Before we begin, please remember to use the Q&A section to ask any question throughout the session because at the end we will dedicate time to answer your questions live. Now, I believe we are ready to start. As I said, we have many attendees all around the world. And I'd like to invite now Jan to begin this workshop. Jan, over to you.
Yes, thank you very much, Katie, for the nice introduction. My name is Jan. I'm a founding engineer at Kumo, and I'm going to talk about the technical basis of how we do time series forecasting at Kumo right now. So I'm quite sure you all know that time series are quite ubiquitous. So no matter if you want to do some economic outlooks, want to forecast sales of your products, want to plan your inventory or your workforce, or maybe even want to do weather forecasting, time series are like almost everywhere, and it makes sense to look at this problem in like a more detail. Oftentimes, you have actually the data for time series forecasting tasks you have given in relational databases, though. Like, for example, here we see like a database that has three tables, a table for products, a table for transactions, and a table for customers. And just from this database, you can already extract like a time series forecasting task, for example, forecasting the daily sales of a set of products that you have in your database. And this will be the running example we are going to look at in this talk because I think it's quite intuitive and easy to understand. So the talk will be structured as follows. First, we're going to introduce time series forecasting on a more high level. Then we're going to look at common forecasting principles. And then we move to how we do forecasting at Kumo with graph transformers. And last, we will have a short outlook into generative forecasting, which is, I think, a quite exciting venture for the future. So let's get started with the introduction to time series forecasting. So time series forecasting at its core is actually quite simple. So essentially you have given a series of numbers, for example, one number at a day, and then you're currently at some time t. And given the past time series, x1 to xt, what you want to do is you want to continue this time series into the future from xt plus 1 to xn, for example, and predict these values and kind of see like how the series of numbers will behave in the future. And if you want to solve this task, then of course, in order to make a prediction about these values in the future, you actually need some kind of signals that tell you like where, how these values could actually behave in the future. And this is the most crucial part of time series forecasting. Like, where do you get your signal from that enables you to do the prediction? And there are actually quite a few signals that you could use. So the most important one is actually the past time series that you have given, of course. So x1 to xt. And this already holds a lot of information about the future. You can decompose this past time series, for example, into multiple components. Here, like in a very simple model, you would decompose it into three different components. And these are, for example, the trend, which kind of indicates the overall direction of the past time series. Then the seasonality, which contains all the seasonal, like periodic components of the time series. So for example, for sales, when they maybe always go down on the weekend, then this would be modeled using a seasonal component. And then you have a residual component, which essentially explains all the rest that is not explained by the other two components. So, but this is not the only signal you can use. So for example, what you also can use is the information about the dates for which you want to make predictions for. So for example, the dates of the future days for which you want to make a prediction, what kind of day it is in the week, or maybe if you have some special information about the day, for example, if it is a holiday, then this is also quite useful to have. But there are much more features that give you some information about the future. So for example, you could have some information about the forecasted entity. In our example, like information about the product. Then you could have information in related data sources of this product. So maybe you know which customers have bought this product, then these customers might also tell you some important information. And of course, there's like general world information, which is also relevant. So if there's a global crisis, then this also impacts your future time series. And all of these features are quite challenging to integrate into a system. And in this talk, we're going to look at these first two, the information about the forecasted entity and the information from related data sources. So with that, let's come to some common forecasting paradigms. And I want to specifically look at Profit, which is a forecasting model by Meta. And this is quite simple and intuitive, which is why it serves well as an introduction here. It follows this decomposition idea that we discussed just now, where you decompose your time series into trend, seasonality, and residual. And it essentially models the time series, the past time series, as a function f of t, where t is the time. And then it decomposes it into individual functions, the trend function g, the seasonality function s, also an event function, which can, for example, model holidays, and then one residual value, which contains all the rest. Now, these individual functions here, they are all modeled using explicit parameterized functions. So yeah, you define a family of functions that has parameters that you need to find in order to fit your past time series. So you can do that. You can fit your model to the past time series. And after you have done that, you can essentially apply it on the future time, like essentially extrapolating the model, which then gives you a forecast that hopefully tells you like how this value will behave if it follows the same functions as it did in on the past time series. But there are a few limitations here. So first, this model does not consider additional information sources. So it really just looks at the past time series and fits a function to it and then extrapolates it. And second, there is also no learning involved. So you cannot really learn over multiple time series at once. So that's why like quite common alternative is to do forecasting with neural networks. And that's what we're going to look at next. So before we actually had an explicitly modeled function. So each of these functions here, they were like given as a concrete explicitly modeled functions with free parameters. And now we're going to move at a setup where we model this function implicitly, for example, using a multi-layer perceptron, an MLP. So this is just a neural network, like for example, a multi-layer neural network, which takes your input, so the time or maybe some additional features, like your specific calendar features, and produces your value in the future, for example. And you can fit this to the model in a similar way. So this is how it looks like. It's essentially describing like a shared function space. So you can put in different t's, different times, and you get like a different value of the forecast for each of these times. Essentially, this multi-layer perceptron models your time series. Now, what you can do with this neural network is quite exciting. So it can be trained over multiple series at once, and it also can take arbitrary other input features that you might have for your data. So what you can then do is you can create a training table which has a lot of different information. So let's say here now we have one row, like each row of this table is one training example, and these for the different products, and then it contains the time for which this is a training example. It contains input features that you might have gathered from whatever information you have. It contains your past sales per day as the past time series, and it contains also a target. Importantly, you can also construct this training table like for different t's. So for each entity, you might choose different t's as example, so that you have more diverse training data over multiple points in time. And then you can train a neural network, which essentially encodes your past using a sequence encoder, and puts that as a feature into this function f, which is also a neural network. And then you minimize like some mean squared error, for example, to train this network to perform point prediction for the future. So this is already one step further. So you can now include like arbitrary features that you have gathered somewhere. Now, what the problem is that relevant data often is stored in some database that you have. And bringing this data that you might want to use for your forecasting task into such a training table format is actually quite challenging and usually requires a lot of manual work. So you need to experiment with the different features. You need to first find out which features are actually useful for your task, which bring any benefit. And then you need to put them into the training table in the correct way in order to make this work. So now we are gonna look at how we can make this easier and how we can reduce these manual steps that are involved here. So that brings us to how we can do forecasting at Kumo using graph transformers. And essentially the goal is, again, we want to really consider all information that you have in your database without manually engineering features that you use as input to your model. Essentially, you just want to describe which value in your database you want to forecast, and then everything else should happen automatically. And in order to solve this problem, we're gonna talk about two different concepts. So the first will be relational deep learning, which is a framework that we presented, which essentially brings your relational database to a graph that you can then use for learning. And the second concept are graph transformers, which take this graph and are able to automatically extract the relevant features, which are then can be used for forecasting. And each of these two concepts I will quickly explain on a higher level, and you're welcome to check out the resources that we have on both of them if you want to know more about them. So yeah, let's talk quickly about relational deep learning. So what you usually have given is just a database. So you have a database schema. And let's say this has these, the schema has these three tables, and it has some links between these tables given by primary and foreign key relationships. Then what relational deep learning does is essentially constructs a graph out of this schema. And this graph is constructed in the following way. So for each row in your original database, you get one graph node. There's also like a time ordering, because usually you have a timestamp, or at least if you have a timestamp in your database, as usually given, for example, in a transaction table, then these nodes also have a timestamp. And then the nodes are connected based on the primary and foreign key relationships of your original schema. Now, this leads usually to a very, very large graph, because the databases are quite large. It's very hard to learn on that. And that's why there's a second step involved where you can extract an entity subgraph for your entity that you are currently interested in. So let's say you want to forecast like something about products, then you can extract like a subgraph around the product that you're interested in, which will then be used to learn on. So if you're interested in relational deep learning, feel free to check out our resources. We have a blog post which is given here as a link, but there's also a paper, an ICML paper from last year. So then the second concept will be the relational graph transformers. And I mean, I'm sure most of you have heard of transformers, and transformers are usually an architecture which originally have been introduced to process sequences of features. It's quite general. So the input to a transformer can be essentially multimodal feature vectors that come from quite diverse types of data sources, which is nice, which we want to use, which is why transformers, it would be very great to use a transformer here. But the problem really is that our graphs are not really a sequence, right? So, and that is the problem that graph transformers are solving. And they do this by providing additional information to the transformer together with like the graph nodes. And these like if, for example, for each node, it encodes also like the table type where this node is coming from, the graph structure underlying these nodes, and also, for example, temporal encodings if these graph nodes have a time component. And that allows you to process like these arbitrary graphs with the transformer, while the transformer is able to understand the underlying graph structure. And again, if you are interested in finding out more about these, then I'm also pointing you to the resources here. So using both of these concepts, we can now move to our general forecasting framework. What we do is shown here. And it all evolves around this forecasting head, which we have also seen before, which is just a function which you can usually model using an MLP. And it receives several input signals. So first, what it receives is the frequency encoded time for which you want to make the prediction in the future. Then you can also include some calendar features. For example, this can be the information if the specific day is a holiday or not. Then you can include the graph features, which come from your graph transformer, and you can encode the features from your encoding of the past time series. And now we're going to look at all these different components in a little bit more detail. So let's start with the past encoder, P. So what it does is it encodes your past time series, and you can use actually different models here, different neural networks to do that. You can use transformers, you can use MLPs, you can use one-dimensional convolutional neural networks, which essentially convolve kernels over the series. And we found that these are actually quite good. They provide a quite good trade-off to encode the past time series, and you can also have a variant which explicitly decomposes the trend component from seasonality components, for example. So you can do that, and then it produces you a feature which you can then provide to the forecasting head for a specific like product in this case. Then we have the date encodings. So we have frequency encodings of daytime and of the day of the week information. So because usually we found that providing like the exact day of the week is very important to almost all forecasting tasks. And you can also provide calendar features, for example, information about holidays or if this day is in other ways special, which might be relevant for your task at hand. So last, we're gonna talk about the graph transformer. So here we receive like a subgraph around the specific product, which is of interest to your forecasting task. So this network is actually is able to pick up features from the relational database, like essentially in a multi-hop subgraph around your product of interest. Now this example here shown is a little bit misleading because what this also allows you is to, for example, look at other products. So you might get to a specific customer here, and this customer then again might have bought another product, and that means you can also essentially share information between products in order to make your prediction. So yeah, I talked about this. So this is our whole framework, and it is important to note that this is agnostic to the structure of the relational database. So it doesn't really matter what kind of tables you have there, as long as it can be automatically processed and these graphs can be extracted, which is true in almost all cases. And it's also agnostic to the specific type and value of that you want to forecast. So you don't need to specifically decide which features to use in your task. The model can find that automatically, so there is no manual feature or data engineering as an initial step. So yeah, we can look at some results here. We can see here, for example, so what we did is we trained our model on a specific business task. And we compared it against Facebook Profit. And while Facebook Profit is actually not so bad in giving you forecasts already in a quite simple way, but you can also see that it sometimes misses the trend a little bit and that it fails to capture higher frequency informations of the time series. So it shows a little bit more mean collapse behavior and less details. And that's what our model is able to do better. It kind of fits to the time series like in a little bit more detail. And this is also reflected in the numbers. If you do a quantitative comparison, you see that we improve on the metrics here in this task. So yeah, last before we close, I would like to talk a little bit about generative forecasting. So this is more like an outlook into the future because I think this will be very relevant in the near future. It's a quite exciting paradigm, and it will be a little bit high level and maybe encourage you to dive deeper into this topic. So usually what we just discussed is we just discussed regression-based forecasting. So we made point predictions with a neural network, and we trained our neural network to minimize this mean squared error here, which we can see here, given some target values that we have. Now this works well if your output is actually Gaussian distributed, then this model is essentially trained to predict the maximum likelihood, so the mean of this distribution of this Gaussian. The problem is though that this really assumes that your output is Gaussian distributed. Otherwise, what this model here is trained to do is not just the maximum likelihood, there might be some other point. For example, if you imagine you have a multimodal distribution instead of a Gaussian distribution, and the mean of this multimodal distribution is actually like in the middle of two modes, then this might actually give you a quite unlikely solution. So that is why probabilistic modeling has a very long tradition in time series forecasting. And what people usually have been doing in deep learning is that they assume some output distribution. So, for example, normal distribution. You can also have like other distributions, like negative binomial, for example, for discrete forecasts. And then you train your model not to predict the point prediction directly, but you train your model to predict these distribution parameters. Here in this normal distribution case, this would be the mean and the variance, for example. And then you train your model to optimize the log likelihood in the end. Now this is quite nice. So it allows you to model a distribution. You can use the distribution to extract quantiles, which gives you like some more information about the uncertainty of the model. But it still makes the assumption about the distribution here. So you need to know beforehand, or you need to assume beforehand what distribution your time series is following. And that is where generative models can come in, because they essentially can model any distribution by just looking at the data without really assuming the distributions a priori. So let's say we can model like this conditional distribution here, which takes all the same inputs as conditioning as we have before. So the temporal encodings, the features, and then it models this distribution, and then it can learn to sample from it, right? And for example, you could use like an LLM to do this. So you could use an LLM to essentially model this conditional distribution, and then you make predictions with it. Now, LLMs would require your output space to be discrete or somehow tokenized. So you would need a token set, a tokenizer. So that's why in here we were going to look at a different approach, which are diffusion models. Because diffusion models actually can learn to sample from very high dimensional and continuous distribution, making it quite general. So essentially what they do is they take a data distribution like here shown on the right, and then they iteratively apply like a forward process which transforms this data distribution into a Gaussian distribution. And then in the second stage, they take a neural network and they train this neural network to reverse this process. And as soon as you have trained the neural network to do that, you can just sample from a standard Gaussian distribution, apply your like reverse process, and that way sample from your original distribution. And it's quite nice. If that's conditional, you can use this to do forecasting. So you just essentially sample random noise, and then you use your model to iteratively denoise it until you reach like some forecast, which is conditioned on your conditioning signals. And that's what we tried also here. So we can extend this architecture in a quite lightweight way to like a generative model, which takes during inference after it was trained, takes a randomly initialized like a time series that you want to predict, and then it iteratively denoises this time series until it reaches your final prediction. As architecture here, you can, for example, use a one-dimensional convolutional neural network again, which just performs this denoising. And I mean, the results are interesting. So interestingly, like the numbers do not really improve, which kind of makes sense in compared to predicting the mean. But it's quite exciting to see that the model is actually able to pick up high frequency details in the time series much better. So if you are struggling with like mean collapse problems, for example, of your time series prediction, then this might be like a really valid alternative to get you more fine-grained forecasts. But of course, I mean, high frequency details, if you get them wrong, they also lead to higher errors, which is usually why in the numbers, quantitatively, on average, the forecasts don't get really better. So I think we will see more of this, and maybe there in the future also more exciting, even more stronger models which use a generative paradigm to solve these tasks better. And with that, I'm going to conclude and let's summarize quickly. So first, we introduced time series forecasting on a high level. Then we talked about Kumo's framework for forecasting, how we brought it to general databases without any manual feature engineering. And last, we quickly also discussed generative forecasting with diffusion models. And with that, I'm going to hand over to Sally, who will give us a live demo of how we can do forecasting at Kumo.
Okay, sounds perfect. Let me share my screen. All right, let's start here. And so when it comes to Kumo, our design philosophy is that we have the most advanced technology, but the setup is really, really simple. And essentially, we ask this question. So what are the most essential things when it comes to prediction? And we identify two things and what we ask from our users. The first is you need to have your data in order to do the prediction. So here, user need to connect your data. And the second essential thing is user need to identify what to predict. So here we have a SQL-like language, which is very simple. I will have a crash course in the next page, which user can specify very precisely what they want to predict next. And under the hood, Kumo will handle a lot of things. It will automatically generate training data. It will automatically choose the model architecture and run experiments to get the best model. And if you are like a machine learning expert or data nerds like me, and you can play with our model plan to squeeze more juice from your data for insights. And that usually can give you additional 10 to 20% gain. And I will show you well in our live demo. And to set up for the demo, so I pick a data set, which is the Austin bike share data set from Kaggle. And it has about 500,000 records and covered the year about like 5 years of data. So you can see it's kind of like a mid-sized database. And so here we're focusing on the first thing user want to provide, which is the data. So let's look at the trips table for the trip. So it kind of like a very like a transaction table, right? So here you have the start time, when does the bike start to have this trip? And you also have the start station ID, have the bike ID, duration, minutes, and different subscriber type. And for the station table, you have some basic knowledge about the station. So here I only have the name here. And according to the data schema, so you can see the two tables can be linked by a common key, which is the station ID here. So a good rule of thumb for using Kumo is that as long as you have two tables and can be linked by a common key here, and then you can leverage our platform. Okay, so this is the first we ask from users. Okay, we got the data. And the next is to tell the platform what you want to predict. And for instance, I will give you a very simple example. Say, what is the daily trip count for each bike station in the next day? So here you are just trying to predict a single point in the future. So here you can just specify for each station in the station ID and predict in the next day the total count of trips it will have. So here you are predicting 1 point. And when it comes to time series forecasting, so you want to know not just the next day, you want to know what's the next 30 days for each day. So here it's very easy to specify that. You only need to say, okay, the forecast length, instead of 1 day here, now we want to predict the next 30 days. Okay, so now we have two things set up. We'll have the data and we also know what to predict. Let's go to our Kumo platform to see what it looks like. Okay, let me show here. Okay, so here, can everyone see my screen? I guess so. Okay, so here is our platform. And so let's start with the data, how you can get the data in. So here we have a connector button. Well, you can just connect to your data source. For instance, if you click add a connector here, you can connect with Snowflake, with S3, BigQuery, Lookup, whatever you want. And here I already have a connector here, which is the Austin bag here. So you can see I connect the data with the S3 bucket here. So once you have your connector, the next thing you need to do is to import the tables here. So that's also very easy. You click add table, choose your connector, use the Austin bag, and then you can select the table you want here. So for instance, if I want to do bike, and will automatically start inferring the column types, and then you can say add the table here, and then the table will be in our system for use. So it's very important to clarify, like we only register the table instead of importing your data to our platform. So your data is still in the data warehouse. So here I already imported the table here. Say we have a station table, and then we also have a trips table, which I have just showed you before. So next step is like, when it comes to prediction, so what we want to do is to form a graph. And this is also very simple to do. Say we already have the station table, and we have the trips table, and we can say name the graph bike. And then what happens next is that we can click next. And then from the station table, we want to make sure that there's a connection between the two tables. I think what happens is like we can choose the trip here, and then we can choose the start station ID here. So now you can see these two tables now form a graph here, and then save the graph, and then you can use it for your prediction query. Okay. Okay, let me use a different name here. Bye. Okay, so the graph definition already exists. So I guess it's because I already have a graph with the same schema here. So now I will just use this graph. Okay, so now we have the graph ready, means that we have the data ready. So the next thing we want to do is say, hey, what we want to predict. And it's also very simple. So for instance, if we start with the bike here, now we have the graph ready. And then what we want to do next is to write our predictive query, what I have showed, which is for each station ID, and we want to predict, first specify, okay, so the unit is for the next day, and then we want to forecast here, the forecast length, we want to change it to 30 to make sure this is a time series prediction. And then we can change the split here to fit to our use case. Okay, here, let's see what question. Timeline. Okay, select timestamps. Oh, I see here. So I do see there are some questions about like, can you predict year over year? So here you can actually specify true here. So the model will learn to predict the data that they have not seen. And also I see a question asking about how can you do neighbor sampling? So here, this is already specified by the planner, but you want to have some fun or experiment with different hops, you can also specify here. And for more advanced users, you can also choose the optimization you want to do and different laws, base learning rate. So there's a lot of things you can play here with the platform. And here, the model is using GNN, but you can also change to graph transformer here to use graph transformer as your model. So as you can see here, if you kind of like want to play with the platform, there's a lot you can play with, but you just want to have a very decent prediction out of the box, and Kumo are able to predict that. So once you have everything set up, looks good, and then you can start training. Okay, so usually it will take about like 30-40 minutes, depending on the yeah. So now what happens next, like you can see, is ingesting data, and the model will start training. And here I have some already trained predictions here. So here, what you're gonna expect is like, okay, take half an hour to do the training, and you have 4 different experiments here, and then you can pick the best model. And you can also monitor the metrics here and see how well each different model is performing. So everything is super clear here. And then after you finish training, let's pull up the results and see what it looks like. So here, this is slideshows. So we have some base case predicted by profit, and this is a result from Kumo. And you can see we have kind of like a lower MAE. So everything here is pretty much out of the box. So we do not do some like additional feature engineering. So what you need to do just to connect with your data and do the prediction here. And as you can see here, for instance, here it's kind of like very smoothed out when it comes to profit. However, for Kumo, it's able to capture some of the nitty-gritties of the things here. Okay, so with that, sometimes people say, hey, I have a question. Now I have some more information about the bike. So how can I incorporate into our prediction? So this is very simple in the sense that as long as you have a bike table and you can link the tables together by this bike ID, and then when it comes to prediction, even when you are writing the same query, the model will automatically pick up the information from this new table and then make better predictions. Okay, so with that, let me hand over to Katie for our Q&A session.
Thank you, Sally, and thank you, Jan, for sharing your knowledge and practical examples. Now we will begin answering questions live. For any question we don't have time to address live, we will follow up via email. And I like to remind everyone to use the Q&A section to submit your question instead of the chat. This ensures that our speaker can easily see and respond to them. Now I'd like to invite Jan to kick off the Q&A session. Jan, could you please read the first question, and Sally, feel free to jump in afterward. Thank you.
Yes, thank you. So let's move to the first question. So Marco asked a great question. So how can we derive confidence intervals from this type of model? And I think there are 2 ways here how we can do this. So the first one is that we use a probabilistic approach, as we have discussed shortly in the talk. So what we do is we assume an output distribution of your model. So for example, it can be a Gaussian distribution if you have a continuous forecast, or like a negative binomial if you have a discrete forecast. Then you predict with your model, you train your model to predict the distribution parameters. You feed them into your distribution, and then you can extract quantiles from this predicted distribution. So that's, I guess, the standard way of how this can be done using deep learning, and that's also what we have if you want to do probabilistic forecasting. The other way is you can actually do it empirically if you use generative forecasting, which is quite nice. So you can use your generative model that you have trained, and you can sample multiple times using your trained model, which gives you essentially multiple hypotheses of how this time series could behave. And then you can look at this and you can extract confidence intervals, or just in general information about the distribution from your samples afterwards. So yeah, I hope that answers the question. I'm going over, giving to Sally for the next one.
Yeah. So another question I saw is like one of the challenge we see with large database schema is that we provide entire database schema as a network, and the training process traverses the whole network. And the question is, have you done work for automatically selecting parts of the graph for specific problems or specific entities, perhaps based on semantic similarity of table and columns? I think there are 2 things here. The first is what kind of data you provide as part of the graph. I think on that part, I think data scientists or machine learning engineer have a lot of knowledge in that narrowing down what specific table we want to use, so that you don't need to kind of like dump the whole database into the graph. Instead, you can provide starting small and iterate later. So you can start with a few table that is truly have a lot of signal. So on the second part is like, once you have the table ready, you don't need to specify, oh, use this, use that. What's going to happen next is like the graph model will automatically handle to learn what is the most critical column they want to learn from. So on that part, the graph model can take care of it. But at the beginning part, the data part, I think data scientists, we have the most knowledge and expertise. Yeah, next, let me handle to Yang.
All right. So here's another question from Omid. It seems necessary based on the type of queries we need to learn a new transformer, or is it just fine-tuning the one that we initiated? So I think this is a quite relevant question. So yes, exactly. So in the base version, what you need to do is as soon as you have a new query that essentially describes a specific forecasting task on your database, you would need to train a new model that you can then apply in like afterwards in different ways. Although like we are also actively working currently on foundation models, and you might have seen Kumo RFM, and that's exactly where this limitation gets eliminated, where you can essentially adapt this model to a new task by using in-context learning. So essentially, you just process your new task like in a feed-forward way by just providing a few training examples to the transformer, which just needs to pass over these examples just once, and then it is kind of adapted to your new task. So you can essentially adapt your model in like 1 second or so to a new forecasting task on your database. And this is quite exciting. Yeah, this is currently like work in progress for the forecasting part, but I'm sure we will have something in the future regarding this. That by the way is also an interesting so that's also a good reason why to use graph transformers, because that allows you to like integrate this method into the whole Kumo RFM architecture, which is based on transformers. So yeah, Sally, go ahead.
Yeah. Another question I see is like, do you have any assumptions on your input data? Yes, we do have assumptions. The first most important assumption is that we assume it's a relational database. So the rule of thumb is like you have two tables, the two tables can be linked by a key here. So this is our most basic assumption. So once you have that, you can do prediction. And when it comes to time series forecasting, obviously you need a timestamp. So I think that's pretty much the bare minimum we need as your input data. Yes. So another question I saw is like how large of the input you can handle. So is there any like scalability challenge? Actually, that's a very good strength for Kumo because we are designed to handle enterprise use case. So for instance, some of our customers, they have billions of nodes and we are able to handle that. And so I don't think the scalability is an issue here. Yeah, next, let me handle to Yang.
Okay. Here's one more question from Sayan for the diffusion head. So he asks, how is the diffusion head trained based on downstream losses only? Because traditionally to generate data, it is trained to remove added noise and allow data similar to inputs, right? And yeah, so it is trained in a very traditional way. So if you remember in the talk, we had our training table, which consists of the past time series, like additional features, and in our case of the architecture, I mean, there are the features coming from the graph and so on. And then there's also the target, and we can gather these pairs that have like input features and targets for like different points in the past in your data, like in our database automatically. So we have full training pairs. So what we can do is essentially we can provide so we can take the target time series, we can add noise to the target time series based on the diffusion forward schedule, and then we can train our model to predict the noise that was added, essentially using that then to perform the reverse diffusion process. So yeah, it's really exactly how diffusion models actually like would be trained, for example, on images. Just that now our data is two-dimensional instead of one-dimensional instead of two-dimensional. Yeah. Heading over to Sally again.
Yeah, I think one of my favorite questions so far, which is like, why do we pick a profit as like a baseline? Because they know like there's so many limits to it. So I think when it comes to machine learning, ultimately what we want to do is there are two things, right? So first is like we want to compare with a very well-known model, and the second is when it comes to machine learning, I think the two metrics like is how well it performs on your real data. So here we really welcome everyone bring your data and test and benchmark on your data so you can have more confidence and in which model performs best.
So here's one more question from Balaji. But we do need a larger amount of data for deep learning, right? Even if I have, say, 10 years of data and aggregated to daily attendance, that still amounts to only around 3,650 records in total. How can we address this limitation? Now, this is definitely true. So there is you need data for deep learning. So there are two parts to this answer that I want to give. I think the first, the tasks that we look at usually, they have a lot of data, not only in terms of data into the past, but also in terms of number of entities that you have data for. So let's say you make predictions for like a whole set of products for forecast, then you not only have like for each of these products the last let's say 10 days, like 10 years, but you also have a lot of different products, and that allows you to train very good models on this data. So this is usually like what you have stored in such a database is usually enough to give you to train such a model. Now, this might not always be the case, of course. So in many time series forecasting tasks, you might not have access to this data. Um, and I think that's still like a limitation. And I would say that one way to address this is exactly using these like using foundation models like tabular or relational foundation models, which are now like coming up at this moment, I would say, which have been pre-trained on huge amounts of data and synthetic data, and which can be adapted to new tasks with just a very few amounts of examples. And that's super exciting because essentially you can take your model and you can just perform in-context learning using just very, very few examples. And then you also don't need that much data for this specific forecasting task.
Okay, I'll answer next question. So the person have two questions. So first is, can you handle missing data? And the second question is, can we export model weights post-training? The first is, yes, we can handle missing data. So depending on the specific type of the data, for instance, if it's a category, and then we'll treat missing data as kind of like a different category. And if it's like numerical data, we'll use mean, but you can also specify specifically in the encoder how you want to handle the missing data. And the second question is, can we export model weights post-training? So the answer is no. I guess it's because when it comes to predicting using your graph, the weights is not enough, right? You also need the subgraph. So what option we provide is like, instead of export model weights, you can export an embedding, which is very powerful to handle like downstream prediction tasks. So a lot of our customers, they train the model on Kumo platform, and then they export the embedding, and then they use the embedding in their production. Say they can use it for retrieval, or they can use it to train their ranking model. So there's a lot of use cases here. Yeah.
Yeah, I'm going to take the next question, but I need to find it. One sec.
While you're trying to find it, I think there's another question, say, are there deployment options for on-prem and on cloud? Yeah, we support both. So we support, you can use Snowflake, Databricks, and you can use on-prem. So we have both options.
Great. So Yushan is asking, is the prediction done on demand or can it also be done in batch manner? Yes, we have batch prediction support. You can like automatically run it as a batch prediction task, also like on a regular fashion. And then maybe I can also move to Vika's question. Dear Jan, the training here is pre-training Kumo RFM with our data, or is it fine-tuning for our task? Are we fine-tuning with our graph? So this, so everything that we showed here is kind of disconnected from Kumo RFM. So the experiments we had here are really like models which have been trained on individual tasks using your data. So essentially, if you want to use this, what you do is you connect the product to your database, and then it can train essentially a model for you on your data, which then is also able to make predictions for your data. This does not use any pre-trained foundation model. But there is no conceptual reason why this should not be possible, and that's actually something that we're currently working on to enable this like to do with the foundation model, and that will allow you to apply to your data even without training and without fine tuning, or you can fine tune using just a few examples to make it even better.
So yeah, let me take this question. So, oh, actually, it's asking you, but I will read the question. Say, dear Yang, the training here is pre-training Kumo FM with our data. What is it fine-tuning for our task? Are we fine-tuning with the subgraph relevant to the task? Can you answer this question?
Yeah, I think that's the one I just tried to answer, but I think the last part actually. Yeah, maybe I didn't fully answer, so I just noticed. So yeah, the subgraphs that are extracted from your database, they are relevant to the specific task that you have described using your predictive query, and that's depending on your database. Yeah. So let me.
Have 7 actually minutes until the end of our workshop, so I believe we are able to answer a few questions more.
Yes.
And as I mentioned at the beginning, for the ones that we don't have time to answer live, we will definitely follow up until the end of this week via email. Sally, are you?
Yeah. Yeah, I'm trying to like going through the questions. I think there's a question from Billy, which is the entity subgraph built for specifically individual task? I think there are two different situations. The first is if it's kind of like a foundation model, the subgraph is the same for different tasks. However, if you are using our enterprise, the for each specific task, we use a different entity subgraph here. So it depends on the model we are using.
Great, thank you. So Jan, are you
Yes.
able to answer?
I can answer some here. So there's one question from Gautam. This may be a silly question. Do we always need a temporal data to use Kumo's technology, or can the data not have any timestamp information, for example, link prediction or user recommendation? So exactly. So we also support a lot of different other tasks using the Kumo platform. So it doesn't have to have time step information. It doesn't even have to be a regression or a forecasting task. So the platform is much more general. It can do link prediction. It can do like recommendation tasks. We also have very like good solutions for recommendation specifically. And you can also do classification, fraud detection, and like yeah, a lot of different tasks that you might imagine on your relational database. And then there is a question from Nathan. How does the Gaussian process differ from generative forecasting? Also wondering if there's a way to predict time series using LLMs and text plus univariate time series data that may substitute independent variables. Yes, so I think Gaussian processes are I mean, they also model the problem probabilistically. They still assume like the Gaussian at some points. I think that's a relevant difference, while diffusion models or like in general, generative models don't assume any types of distribution. Now, that doesn't necessarily mean that they're always better. So sometimes, I mean, if you actually have like data that follows your assumption, then these like Gaussian processes, for example, might be a very valid thing to do because they also like give you much more guarantees and information about the predicted distribution. And then the second part was about LLMs, and I'm pretty sure you can use LLMs for time series forecasting, and I think there are also research works about this, doing that. So what you need to do, of course, is you need to tokenize your output space so that you have a discrete set of potential outputs that the model can then essentially predict. And then you can either fine-tune your model or you can do in-context learning for specific time series and can use and can essentially adapt an LLM to do that. Although I'm pretty sure that they are not really good to do time series forecasting if you just do in-context learning. I think you need at least to fine-tune them for the specific task. But yeah, I might be not aware of some newer works here in that area. So
Thank you,
Yeah.
Jan.
So yeah.
Thank you. So since we have 3 minutes until the end of our workshop, are you able to answer one more question before we end the event?
Yeah, I can answer this question. So how effective is this algorithm while dealing with highly intermittent data, for instance, over 70% zeros in sales sequence data? So here, I want to say this data is intermittent. It's just like the prediction here we want to make is like, it's possible there are many zeros. So I think this is a prediction task that the model are able to pick and build into its prediction. So if you have over 30 zeros, meaning that the sales volume is zero for that case, and then the forecasting model will be able to predict, say, in the future timestamp, this is going to be zero. So I wouldn't think this is a problem here.
Amazing.
all right.
Thank you. So Jan, do you have maybe something that you would like to answer or?
Yeah, there's one more thing from like one more question from Marco I can try to answer. I suppose we can use this for multi-dimensional time series forecasting, right? But one model per time series? No. So yes, you can use it for multi-dimensional time series forecasting when you don't need to necessarily have one model per time series, but you can do either. You can have directly like multiple channels for each entity, or you can just model the problem that you have one entity per channel. So essentially, then you have one model which trains which is trained to predict all of the channels at the same time, and it can also essentially share information between the two, like between the multiple channels of the time series.
Thank you, Jan. Thank you, Sally. We've reached the end of our workshop. I would like to say thank you for everyone that joined this session and for your amazing question and positive comments. I hope you gain valuable insights. Tomorrow, as I mentioned in the chat, I will send you an email with the video recording and free trial links and additional helpful links. And thank you once again for your time and attention, and have a great day. Bye.